Good morning. Welcome to Krishna's classroom. This lecture, we introduce the concept of uniform integrability. That means the integrability criteria for a class of measurable functions taken all together. Okay, just like uniform convergence or uniform uniform convergence, etc. Well, it resembles mostly the so-called equicontinuity and so on. Okay. That is the better analogy that you have, but it's clear how it is coming up. So we introduce uniform integrability and a consequential result, the Vitali's convergence theorem. That means what we show is that if for a sequence of measurable functions on a set of finite measure, if it satisfies the uniform integrability criteria, then limit n tending to infinity integral over E Fn equal to integral over E F. Essentially, you say that the interchange of integration and the limiting process is valid. Okay, so before we come to that theorem, let us prepare the background and we shall define what is uniform integrability. The definition. Let script f be a family of measurable functions on a measurable set E on E then F is said to be uniformly integrable if what it says is the following. For each epsilon positive, there exists a delta positive which depends on epsilon such that for any f if A is a measurable subset of E with measure of A is less than delta, then integral over A mod f is less than. Okay, so what does this say? So we are given a family of measurable functions, and we say that f is uniformly integrable over E if the following criteria holds. That means for an epsilon positive, you can find a delta positive, and delta depends on epsilon only and not on the function. Okay, such that for any f belonging to f, if we take A to be such that measure of A is less than delta, then integral over A of finite. It says that this delta depends only on epsilon and not on f. That's so for the entire collection of f, now this property is valid. Okay, so it says the following. Now you see that let us draw a very innocent figure. This is not properly the thing. Now what it says is that you are actually computing. Suppose this is your A with the measure of A is less than delta. It's a very simplistic figure, and then what you say is that this is f. So this is the area that you are computing, and I have taken f to be positive. Otherwise, we are taking mod f here. Sorry, I think I should write here less than epsilon. Okay, so what it says is that the area that you have here is less than epsilon, and whenever the length of this set A or the measure of this set A is less than delta. But that does not depend on f, because you have a bundle of functions like this of this class. Then you are talking about uniform integrable. That's the whole idea. Okay. Now we'll give an example. It is an example where, of course, it says whether this is true or not. So let G be a non-negative integrable function over E. Now define f to be the collection of all f is measurable over E, and G. Then F is uniformly integrable. Now this is quite easy to see, because you see that corresponding to G is a non-negative integrable function. Therefore, what does it say? Have given epsilon positive, there exists a delta positive such that if A is a subset, a measurable subset of E of measure less than delta, then integral over A of G is 0. So, for G integrable, right? Epsilon positive such that for any A measurable and measure of A is less than delta, integral over E G is less than. So this is that. Okay. So that comes from the integrability of G. Now what you have is this. So by simply now mod f is less than or equal to G. Hence integral over A mod f is less than or equal to integral over A G, and that is less than. Okay. So how we have picked the particular delta? So the delta, now this is valid for every choice of epsilon. For epsilon, there is a corresponding delta, and for any A with measure of A is less than delta, this inequality is valid. Therefore, you see that f is integrable, or the whole collection of f is uniformly integrable. This is true for every f belonging to okay. Therefore, now this follows from monotonicity of integrals. Okay, therefore that is clear. Now we make an observation. This is again a very simple result that you can prove. That means if you take any finite collection of integrable functions over E, then that collection is uniformly. That's the next year. That's a very simple thing. But you cannot make that statement about infinite collection. Okay. So next year now. Something I don't right. Left. F K be a finite collection of integrity where E is measurable. Then the collection Fk is uniformly integrable. Now this is quite easy to prove. So for any k, for each k, 1 less than or equal to k less than or equal to n, what we have is this. Given epsilon positive, there exists a delta k positive. Delta k depends on Fk actually. Okay. Positive such that for any measurable subset E, A of E, with the measure of A less than delta k, integral over E of integral over A of epsilon. So for any given epsilon, epsilon is the same for all the functions f1, f2, etc., fk. We can find a corresponding delta, and that delta would in general depend on f. Okay, so we designate with delta k. So whatever is that, since these functions are integrable, so you get delta k positive such that for any a with the measure of a is less than delta k, this is true. Now what you do is choose delta to be equal to minimum of because there are finitely many, the minimum exists. Okay, so you choose this as your delta. Then it's clearly then for the given epsilon positive, choosing delta as above. For any a with measure of a is less than delta, over A Fk is less than epsilon for this is because, see, here you have delta is less than delta k, then this is valid. Okay. So this is true universally for once you choose measure of A less than delta. Okay. Therefore, because you cannot make the same statement for a countable collection of functions or infinitely many functions simply because this step won't be valid. Okay, right? All the deltas are positive, therefore if you choose the infimum, that is going to be probably 0 sometimes. So that's true. Okay, so that is clear. Now we state a part of the, or prove a part of the Vitali theorem. Okay, right. So the next theorem is this. This is a part of the Vitali theorem. Assume E has finite. This is the assumption. It's finite measure. Let be a sequence of functions measurable and uniformly integrable over E. Over E. Then F integrable over. So what we have to prove is the following. We have made a statement be a sequence of functions over E. Let me state it properly, such that if converges to F pointwise almost everywhere on, then F is so that's a statement of the theorem. Now what we have is this: you are given a set of finite measures. Z is a set of finite measures, and Fn is a sequence of measurable functions which is uniformly integrable. That we are imposing the condition that it is uniformly. See, this is a countable collection in general, uniformly integrable over E. So if Fn converges to F pointwise almost everywhere on E, then F is integrable. So this is the result that we want to do. Of course, you are not assuming E is bounded or anything, but E is assumed to be a set of finite measure in that sequence. Okay. So the idea is this. Okay, what you can infer is that. So what we first infer is that F, this is uniformly integrable, this collection. Therefore, given epsilon, there exists a delta. Okay, so that we okay. So and then for each set of measure, subset A of measure, finite measure less than delta, you have the integrability of F over A. So that we are going to make use of to show that it's integrable over the K. Okay, so let us do this. Proof is, let epsilon be chosen as 1. Then there exists a delta naught positive, which is the delta choice of, it's a specific epsilon that we choose, and you have the corresponding delta which is designated by delta naught. Okay. And now we apply the uniform integrability criteria. Delta naught, you have integral over A mod F less than 1 for each n. This is the outcome of that. Now this is, we use uniform integrability. Okay. Now you see the measure of E is finite. Therefore, express a finite collection of subsets of E, say K equal to 1 to n finite number, which is a disjoint collection, because we have seen that any set of finite measure can be written as the union of a disjoint collection of measurable sets. The length of each of these collection is as small as we please. Okay, so given delta, you can find a corresponding collection. Okay, such that this is true. Therefore, what we have? So we are choosing such that for K equal to, now this is what, and these are all disjoint collection. Therefore, now we use the additivity over the measurable sets. So what we can immediately conclude is that for any n, integral over E is equal to sigma K equal to 1 to n, because what you can do is you can write this as integral over union K running from 1 to n, and that is equal to Fn, and that each of this is less than 1, therefore this is less than Okay. Now what you do is, see, f is the point-wise almost everywhere limit of f. Therefore, point-wise on E almost everywhere. We have by Fatos's lemma. Just apply this Fatos's lemma. What you get is this. It is this. By Fatos's lemma, you have integral over mod f is less than or equal to mod fn, and this is for each n, this is less than n, therefore this is that is f is integral. So we have proved one part of the statement of the Vitali's convergence theorem. Now we are in a position to state this and then concentrate on the proof of the main part of the Vitali's convergence theorem. The Vitali's convergence theorem. Let E be a finite that means measure of E is finite. Suppose the sequence of functions is uniformly over E. Almost every point-wise, almost everywhere. In this part we have already proved, and limit n tending to infinity, integral over E. And f is essentially limit n tending to the pointwise limit of fn, okay, which amounts to saying that you can interchange the integration and the limit. Yeah, one of the things that you should see, we have in the previous proof, we have used the result that if E is a finite measure and delta is some positive number, then you can express E as the disjoint union of a finite number of sets, measurable sets, each having measure less than delta. So for any delta you can do that. Delta is small, then correspondingly there is going to be some number n. That's what I just want to remark at this stage. Now if you go through the statement of the Vitali convergence theorem, we are assuming E is a set of finite measure and Fn is a sequence of real valued functions which is uniformly integrable over need not be real valued function, it can be even extended real valued functions. If Fn converges to the sequence Fn converges to F pointwise almost everywhere, that means except possibly on a set of measure 0, if it is convergent pointwise to F, then F is integrable, this is the statement, over E, and this is true. That means the integration and the limiting process can be interchanged. Okay, so if you look at compare with the previous theorem, then you see that you have all these conditions assumed, and therefore the first part of the statement comes from there. Okay, so the integrability of F over E follows from the previous theorem. The integrability follows from the previous theorem. Okay, so that part is done. This part is done now. F is integrable over E. Now all that remains to be proved is this. How do you approach this generally? Generally this is what you do. So you take the difference of the general approach to proving the second part. Is to show that this can be made arbitrarily small by choosing this is what you want to. So this is our strategy. We are going to work on this. Now, one of the things that you have to observe here is that Fn converges to F point-wise almost everywhere, which means that there are sets of measure 0 over which Fn may not converge to F. Okay. So what you do, you use our usual strategy. What is that? You excise those points from E. So you get E minus or E slash some set of measure 0 over which Fn converges point-wise to F. Okay, and whatever proof that we do right now can be applied for that, and whatever happens on the other part, that is on integral A, is immaterial because it doesn't contribute anything to the integral. Okay, therefore, what we do without loss of generality, we will assume. So, F1 F point-wise on E, everywhere on E. Told you the strategy. The strategy is that what we were using all along. Now the strategy is, if we have proved this on E, now you see you have these conditions valid in general on E slash A, where the measure of A is 0. So doesn't matter what happens on set of measure 0. The contribution of that from that portion to the integral of f is going to 0. So we don't have to bother with that. Okay. So what we do is, therefore, the strategy that we use here to prove the result under this condition works on E slash A. That's the idea. Okay. So let us work on this. For any set any measurable set E and any natural number N, what we have is this. Let us estimate this. This is our strategy, and this, is equal to bilinearity and of the integration, and this is of course less than or equal to and this you can split into integral over slash a. A is a subset of E, and that is less than or equal to plus integral over a mod fn so this inequality is there. This is in general true for any measurable subset A containing. Now let us start making each one of these small. Okay. Now what we do is we are going to work on this and we use this uniform integrability. So right. Now let epsilon positive then we want to make this less than epsilon by choosing n sufficiently large. That is the strategy. By uniform integrability of when there exists delta positive such that integral over a mod fn is less than epsilon by 3 for any measurable set set A with measure of A less than stand. Therefore, now we apply Fato's lemma. We have integral over E and that is less than epsilon by. So this part, where is that? The This part we have estimated, and this is of course is already estimated, and therefore we have to say something about this one. So f is real value this is the point. F is real value and E has finite measure by Agrov's theorem there exists a E such that measure of E naught is less than delta. F1 converges to F uniformly on E naught. So that is the outcome of the or that is what. So it said what we have said is that the point-wise convergence almost everywhere is what you call Fn converges to F nearly uniform. That is the outcome of the Agrov's theorem, application of the Agrov's theorem. That is Fn converges to F This is what we have made use of. Now we have to work on this one. So I am trying to get the estimate of this. So that's why you have this E slash E naught, where measure of E naught is less than delta. Okay. Therefore, what you have? Now choose such that such an n exists such that mod Fn minus F is less than epsilon divided by measure of E is finite, and you take this. That is possible. Such a choice of n is possible on where Fn converges uniformly to F. This is coming from uniform E slash E. Okay. Now use that estimate. So we have nearly everything in our hand. What do you have? Now you see the A that you have, you can choose as E naught. Therefore, what you have? Now take A equal to E naught. That is appearing in the context of the application of the Agraff's theorem. Then we have this integral over E is less than or equal to this inequality is there, and this is less than, you see, this part is less than epsilon divided by 3 times ME. So we use that. Therefore, what you get? So this is less than epsilon divided by multiplied by measure of E naught. And this is, of course, what you have, measure of E is finite anyway. So therefore, this is going to be this part, a measure of E slash E naught divided by measure of E is going to be less than 1. Okay, plus by our choice epsilon by 3 plus 8. So this is less than . So that completes the proof. Okay, so that is the proof of the Vitali's convergence theorem. Now I think I will stop here and then make some further remarks about it in my next lecture. Thank you very much.